Good afternoon, dear college. My name is Anastasiia Driagina. I am laboratory researcher from Ural Federal University. Today, I would like to present to you our result on the synthesis and magnetic properties of nanowires at thin film anodic alumina. Nanowires offer unique flexibility in tuning their magnetic and electric properties, which make them one of the most promising class of magnetic nanomaterials for numerous applications. Magnetic nanowires, together with many other nanostructure with shape-driven properties, attract significant attention due to their unique properties, which can be used in a wide range of applications, such as information recording, spintronics, sensors, and integral systems, and so on. We are particularly interested in obtained nanowires in a thin layer of alumina oxide with the possibility of making contacts to both sides of the sample. The main goal of our work was to offer a simple yet flexibility way of producing a nanowires array embedded into a thin alumina layer synthesis on semiconductor or the electric substrates with electrical contact on both ends. In this work, we focused on synthesis of nanowires of different compositions: cobalt, nickel, and cobalt iron. Cobalt or nickel iron alloys in thin alumina film deposit onto the glass substrates, and synthesis of magnetic nanowires by direct current electrodeposition and analysis of their magnetic properties. You can see the task on this slide. I will go over tasks throughout the report. I would like to start with synthesis techniques and experimental procedure. The synthesis of nanowires can be divided into two stages. However, let's say the zero stage is to make the base. Fabrication of thin film aluminum by iron sputtering, aluminum thickness 2 micrometer. So first stage synthesis is producing porous template of anodic alumina. We used standard anodization for producing porous template, and at the end of the anodization process, the bare layer is thinned. The second step in the creation of nanowires is electrodeposition on alternate IC or DC mode. On the right slide of the picture, you can see a scheme of what the pores of alumina look like. They are fairly well ordered. This is the barrier layer. For AC electrodeposition is must to be thinned, and for DC electrodepositions it must be completely removed. On this slide, you can see the scheme of installations for the synthesis of nanowires. An oxalic acid solution was used as the electrolyte. Anodization was carried out at room temperature, and the electric voltage was 40 volt. At the end of anodization, the procedure of thinning the barrier layer was used by gradually reducing the electric current and reducing the electric voltage at minimum current. For deposition on IC mode, the voltage is lowered to 8 volt. For DC mode, to the minimum is possible about 3 volt. Electrodeposition take place in the same using the electrolytes you can see on the slide. The process takes place with AC mode with characterization of 12-volt and 200 Hz, and for DC mode of the 3-volt. We conducted a study and obtained the depends of where concentrations of iron in nanowires on where concentrations of iron surface in solutions. We got such depends that you can see on this slide. It can be seen that the layers sections for the cobalt iron compound are up to 30 atomic percent, and for nickel iron compound up to 40 atom percent approximately. This is necessary to obtain certain compound in the future. On this slide, you can see an example of nanowires hysteresis loops for iron nickel and iron cobalt compounds. Nanowires in an alumina matrix are naturally ordered. Their figure shows the hysteresis loops of the corresponding sample. As you can see, the corrosive field, when measured along the axis of the wire, turns out to be relatively high, as well as the remnants, which indicates the presence of a different axis of easy magnetization along the axis of the wire. When a magnetic field is applied perpendicular to the nanowires axis, a significant decrease in the corrosive field and remained magnetization in observed. The observed anisotropy is the result of the presence of three main contributions: magnetocrystalline anisotropy, shape anisotropy, and magnetoelastic anisotropy. Next on this slide, you can see the hysteresis loops for the array of nanowires obtained in DC mode. It is clear from the shape of the loop that it was possible to deposit nanowires is the direct current mode, but the distributions of nanowires is most likely in homologizations, and not all pores are well filled. Necessary future refinement of the process of creating nanowires in this mode. And so as a result of our work, a technique for obtaining nanowires is in thin layer of aluminum oxide was developed. Arrays of nickel cobalt nanowires and different compounds were obtained, and their compositions was determined. A study of the magnetic properties was carried out. Hysteresis loops of the obtained sample were obtained. It was show what nanowires in the template are naturally ordered, and the easy magnetization axis line parallel to the axis of the array of nanowires, and the beginning of the producing of an array of nanowires in the DC mode has been laid. In the future, we plan obtain more nanowires using these techniques, and obtained arrays of nanowires with electrical contacts connected to both end surface, and more detailed study of the magnetic properties of obtained arrays of nanowires. Thank you for your attention. I'm ready to answer your question.
I didn't see any questions in the chat, but I'm ready to see mine. Oh, yes, I saw it. Thank you. What are the minimum and maximum diameters and lengths of these nanowires?
Okay, I understand questions. Minimums wide about 35 nanometers, and maximum weight is about 130 nanometers, and we can create, but in this sample we make nanowires about weight about 40 nanometers, and height about 200 nanometers.
Okay, thank you. And one small question, is it possible to use wires as tubes? I mean, not wires, but maybe matrix, alumina matrix that you use
You
for the
can,
creation.
I don't understand questions. You can repeat, please.
As I understand, your matrix was chemically destructed during the creation of the wires. Or you can save the matrix and use it as a porous
why porous
liquid.
have with ordered? I don't understand.
No, can you use it? Can you use it as porous matter?
Yes, for synthesis nanowires, we use porous in alumina template, and with electric depositions, we make our nanowires. If I right understand question.
Can you use these porous after the creation, the wires?
Okay, we removed with porous, for example, or maybe we I don't know how to say. We use with porous only for deposition nanowires.
Okay, and small questions. What is the interpore distance in your array of wires?
Distance between
Pores.
Okay, I understand. About 100 nanometers for diameter nanowires, 40 nanometers.
Twice larger. Okay, thank you so much. Thank you for your talk.